In an earlier presentation, we talked about the relationship between asymptotic internal stability and BIBO stability. We said that asymptotic internal stability implied BIBO stability. That is, the set of asymptotic internally stable systems lies inside the set of BIBO stable systems. And we said that the reverse is not always true, although it usually is. In this lecture, we want to talk more about this problem: why BIBO stability does not imply asymptotic internal stability. The key to understanding this lies in the difference between internal and external system descriptions. When we look at an input-output relationship, that is an external system description. When we look at all of the behavior of the system, including the behavior of the variables within the system, then that is an internal system description. For this purpose, I will use the analogy of a house and its occupants. Hopefully, this will help you understand the difference between internal and external system descriptions and why BIBO stability does not imply asymptotic stability. Let's now define things a little more precisely. An external system description is a model that only describes how the input affects the output. On the other hand, an internal system description describes how all signals in the system respond to their initial conditions and to the inputs that are applied. So the internal system description describes everything that's going on. So let's now consider the analogy of a house and its occupants. For the external system description, we just see what the occupants send out in response to whatever we send in, our input. For the internal system description, we not only see how the output is affected by the input, but we also see what's going on inside the house. So let's now meet our homeowners. Yes, it's Molly and Morgan Mode. And as you can tell by their t-shirts, they are very stable people. They always pay their mortgage on time, they have a great credit rating, they don't let the dishes pile up in the sink, and they're both yoga instructors. So let's see how the house system behaves with Molly and Morgan as the occupants. And we're going to assume for this analysis that neither Molly nor Morgan is a hidden mode. So we can fully observe what they're doing, and we know that they'll respond to their initial conditions and to the input. We'll put in a nice input to this system, and we'll see what the output does. So we're looking at external stability. And our nice input is a letter. Dear neighbor, please accept this gift of herring and bowling shoes. Sincerely, Professor Knospe. How will Molly and Morgan act in response to this letter? Since Molly and Morgan are nice, stable people, they send back a nice letter. This is what external stability is like. We send in a nice input, we get a nice output. So the house system is bounded input, bounded output stable. We put in nice inputs, we get nice outputs. And it's BIBO stable because Molly and Morgan both have their characteristic values less than 0. As I said, they are stable modes. Now, since Molly and Morgan are stable modes, we know they respond well even when there's not an input. They respond well just to their initial conditions. So, even when I don't send a nice letter in, they might send a nice letter out. And they certainly wouldn't send a nasty letter out. No, not these guys. This nice response to initial conditions is the hallmark of internal stability. And the mode's house is internally stable because their characteristic values are in the left half plane. Let's now broaden our analysis and not assume that the modes are not hidden. Let's now consider the different ways that the house system can respond to an input if one of the modes is hidden. And there are 4 cases here. The first case is the one we looked at before, where neither mode is hidden. In cases 2, 3, and 4, Morgan is a hidden mode, but he is a stable guy. So what does it mean to say that Morgan is hidden? What this means is that he either does not respond to the input or does not contribute to the output, or both. So we can imagine this in the following way. Perhaps Morgan is wearing earphones, so he can't hear the input. He can contribute to the output, however. Or perhaps Morgan has tape across his mouth. He can hear the input, but he can't respond to the output. Or perhaps he has both earphones and tape across his mouth, in which case he doesn't respond to the input, nor does he contribute to the output. So let's introduce some terminology. A mode that responds to the input is called a controllable mode, and a mode that affects the output is called an observable mode. So, in our cases here, 1 through 4, Morgan is controllable and observable in the first case. He is uncontrollable yet observable in the second case. He is controllable but unobservable in the third case. And in the fourth case, he's uncontrollable and unobservable. However, Molly mode is controllable and observable in all 4 cases. She will respond to the input and she will have an effect upon the output. We can also talk about whether a system is controllable or observable. If any mode of a system is uncontrollable, the system is said to be uncontrollable. So, in cases 2 and 4 on this page, the system would be uncontrollable because one mode, Morgan, cannot respond to the input. If any mode is unobservable, the system is said to be unobservable. To be observable, all modes must affect the output. Systems 3 and 4 on this page would be unobservable systems because Morgan cannot affect the output. To summarize then, for our 4 cases, the system is controllable and observable in the first case, uncontrollable but observable in the second case, controllable but unobservable in the third case, and uncontrollable and unobservable in the fourth case. Since the system's characteristic values are in the left half plane, we know the system is asymptotically stable, and any system that's asymptotically stable is automatically Bibo-stable, independent of whether the system is controllable, observable, or neither. To make this more concrete, let's actually put together some real problems. So let's suppose we have a system with 2 modes, and Q of lambda is lambda squared plus 3 lambda plus 2. We find the roots of that characteristic polynomial as lambda 1 equals -1 and lambda 2 is -2. And therefore our modes are e to the minus t and e to the minus 2t. Since lambda 1 and lambda 2 are in the left half plane, we know these modes are stable. Here you can see example systems for each of the 4 cases we examined. The first one is controllable and observable. The second one is uncontrollable yet observable. The third one is controllable yet unobservable. And the fourth one is uncontrollable and unobservable. In the example systems, the input signal is X and the output signal is Y. Z is an internal signal of the system. I believe it would be difficult for you to see the controllability and observability, or lack of, in the example systems. So for now, you'll just have to trust me on this. Once we introduce the Laplace transform, we'll review this material again. The important thing right now is that you understand these concepts. Let's now look at a different scenario. Someone is coming to visit Morgan and Molly. Someone very different. It's Molly's crazy uncle Modric. He's very unstable. Modric wanders around the house all day, mumbling to himself. Morgan and Molly will be happy when he leaves at the end of the week, but for now, their house contains 2 stable and 1 unstable modes. You can tell that Moderick is unstable because his characteristic value is in the right half plane. So let's examine our 4 scenarios now that Moderick is visiting. Since Moderick is an unstable mode, the house system is now asymptotically unstable. It's also Bebo unstable, since Moderick is not hidden. The controllability and observability of the 4 cases has not changed since the last time we looked at it. The controllability and observability is determined by the hidden mode, which is Morgan. The asymptotic instability of the house, now that Moderick is staying with Morgan and Molly, is apparent. Even with no input to the system, we're getting outputs that are rather crazy. Let's now consider some cases where both Morgan and Moderick are hidden modes. That's cases 2 through 4 on this page. In all the scenarios below, we're going to have asymptotic instability. That's because Moderick is an unstable mode. Doesn't make any difference whether he's hidden or not. The house system is asymptotically unstable because this is internal stability. Internal stability means that we can see all the things that are going on inside the house. We're not just looking at an input-output relationship. So, even though Moderick is hidden, his crazy behavior means the house is asymptotically unstable. But if we consider Bebo stability of our 4 cases, well, that's a different story. And the reason why is Bebo has to do with external stability. External stability is about how the output responds to the input. So, if Moderick is a hidden mode, either because he's uncontrollable, unobservable, or uncontrollable and unobservable, he's not going to affect the input-output behavior. If Moderick can't hear the input and can't contribute to the output, well, he can't affect the input-output behavior of the system, even though he's unstable. So in cases 2 through 4, the system is asymptotically unstable, but Bebo stable. In case 1, however, the system is Bebo unstable and asymptotically unstable. Let's look at that case 1 again, where Moderick is not hidden. We'll test the system for Bebo stability. We'll put in a nice input and see how the output responds. Our nice input is a letter. Dear Moderick, please come to my house for dinner tonight. We'll drink a 1961 Chateau Latour. Sincerely, Professor Knospe. What will Moderick do? Moderick did not respond well to our nice letter. Scenarios 2 through 4 show why Bebo stability does not imply asymptotic stability. In these scenarios, the house system is asymptotically unstable because Moderick is living there. But they're Bebo stable because Moderick is hidden. He has no effect on the input-output relationship. Let's try to summarize all these ideas by referring to our Venn diagram for asymptotic stability, Bebo stability, and Bebo instability. And we'll look at 3 cases here. And this doesn't represent all possible cases, but it does represent cases that belong to each of these sets. So in case A, we have Molly as not hidden, and Morgan and Moderick as hidden. This is an example of a system that has Bebo stability, but is asymptotically unstable. It's asymptotically unstable because of Moderick. In case B, both Morgan and Molly are not hidden, and since Morgan and Molly both have their characteristic values in the left half plane, this system is asymptotically stable. Now, if either Morgan or Molly were hidden, that wouldn't change anything at all. It would still be asymptotically stable. In case C, we have Morgan, Molly, and Moderick all not hidden. And this is an example of a system that is asymptotically unstable because of Moderick, and also Bebo unstable because Moderick is not hidden. Another example for case C would be Morgan, Molly, and Moderick living in the house with Morgan or Molly as hidden modes. To close this presentation, let's see how well you're understanding this material by having a pop quiz. The question is, true or false? If a system is Bebo unstable, it cannot be asymptotically stable. Please take a moment to think about your answer. Okay, this one's a bit tricky, because in the lecture I gave you a condition which said that if you had asymptotic stability, you had Bebo stability. And I said the reverse does not hold. But here we're talking about instability. The question is, if a system is Bebo unstable, it cannot be asymptotically stable. True or false? And the answer is true. Any system that is Bebo unstable must have a characteristic value that is not in the left half plane. And any system that has a characteristic value that is not in the left half plane cannot be asymptotically stable. This is easy to see from the Venn diagram that we've been looking at. If a system is Bebo unstable, it lies in the blue region. So for example at this star, and that's clearly outside the set of asymptotic stable systems. To close this presentation, let me give you a procedure for determining Bebo stability. Now this procedure will only work for a certain class of systems, those that are linear, time invariant, and described by ordinary differential equations. So you're given the differential equation q of d times y of t equals p of d times x of t. You do not know whether this system is controllable or observable. How do you determine whether it has Bebo stability? First, you'll determine whether it is asymptotically unstable by examining the roots of q of lambda equal to 0. Is it asymptotically stable? That is, are all the roots in the left half plane? If the answer is yes, then the system has to be Bebo stable. If the answer is no, you'll have to find the impulse response of the system, and then check the integral condition for Bebo stability. If the integral is finite, then the system is Bebo stable. If it's not finite, then it's Bebo unstable. The advantage of this procedure is that you're going to do an easy check first for asymptotic stability, and perhaps you'll get the answer right there and not have to find the impulse response. This procedure will become a lot easier after we introduce the Laplace transform. In our next presentation, we'll look at how the characteristic roots affect another aspect of system behavior, specifically the time response of systems.